All right, folks, section 4.5, we're going to discuss a topic called optimization. And I'm going to start off by making a comment that I don't know if you've heard me say this yet, but read the section. It's a well-written section. I encourage you to please read the section. I'll specifically call out examples 1 and 2. I think those are decent examples. I think they're well-written examples for the book. You'll also find guidelines in the section that I think are pretty solid guidelines. In fact, I'm going to go over the guidelines right now. So you'll see this in the section. Guideline 1, it says, read the problem carefully. I can't stress that enough. Read the problem carefully, slowly, carefully. In doing so, identify the variables and organize the given information with a picture when appropriate. Not always going to be drawing a picture, but a lot of times you will. Then you're going to identify the objective function. Now, the objective function, that's just a nice way of saying the function that is to be optimized. So in an optimization problem, you're trying to maximize something or minimize something. That's called optimization, when you're trying to maximize or minimize something. So you want to have a function that's trying to represent what it is you're trying to maximize or minimize. That is, optimize. And then you're going to write the function. You're going to write it in terms of the variables given in the problem. Guideline 3, identify the constraints. There might be some constraints given that you're going to write those constraints in terms of the variables of the problem. Sometimes it's necessary, so I'm up to guideline 4, that you have to use the constraints to eliminate all but one independent variable of the objective function. So let me just stop right here. Let's say we're trying to maximize area. Well, we know area is length times width, and if you've labeled a rectangle, if you've labeled the length as x and the width as y, you would have area equals x times y. That's two variables. You need to turn that into a function of just one variable so that you can do calculus on it. And that's where a constraint equation would come in. So maybe in this mythical problem I'm talking about, maximizing area, maybe you're given some constraints on what the perimeter could be. And the perimeter of a rectangle is equal to 2 times the length plus 2 times the width. So that's what number 4 is talking about. Number 5, write the objective function expressed in terms of a single variable. And sometimes, you're going to have to find an interval of interest for that variable, because if you find an interval of interest, and this is the key thing, it kind of brings in everything that we've discussed, that if it's a closed interval, well, we know how to find the absolute max and absolute min on a closed interval by using the 5-step process we saw earlier in the chapter. Whereas if it's an open interval, well, then we're going to have to rely on the second derivative test. Remember when we saw the second derivative test, I mentioned its usefulness would come about in a later on section called optimization. Well, here we are. And then the 6th step, we use calculus to find the absolute max or absolute min value of the objective function on the interval of interest. It says, if necessary, check the endpoints. Well, it depends on if it's a closed interval or open interval. So let's look at an example. I really only have one example because, it's not possible to do an example of every type of optimization problem. It's the process. The process is what's important. You have to battle with reading the problem carefully and coming up with the objective function on your own and any constraints that are involved. So I think we can do one example to show you the battle, but I can't do an example of every type of optimization problem out there. There isn't enough time. I'm talking about there's not enough time in the world. You never know what you're going to see, but it's the general process. So this example I have, it's kind of a classic one. Suppose an airline policy states that all baggage must be box-shaped with a sum of the length, width, and height to not exceed 108 inches. What are the dimensions and the volume of a square-based box with the greatest volume under these conditions? So I'm going to head off to the chalkboard to work through it, but please write down all these words because I'm going to be referencing it when I get to the chalkboard. And before I head off to the chalkboard, I'm kind of looking at it, and it says, what are the dimensions and volume of a square-based box with the greatest volume under these conditions? So it looks like I'm going to try to maximize volume. That's going to be my objective function. So here I go, off to the chalkboard to work through this one. All right, this example of optimization, it's an airline policy that baggage must be box-shaped. The sum of the length, width, and height can't exceed 108 inches. What are the dimensions and volume of the square-based box with the greatest volume under these conditions? We looked at some guidelines and stuff, and I drew a box, nothing fancy, but I think it can kind of help me on this problem. So let's kind of pull out the information. We know the box has to have, a square base. So that means each dimension on the base will be the same. So I'm generically going to call the base, it's x by x. Then its height, I'll just call that y. Now, what is it we're trying to optimize? What is it we're trying to maximize? It's the volume. That's what we want to maximize. So our objective function, that's what we want to maximize, is the volume. So we know volume is length times width times height. So for this box, the volume is length times width times height. That's x times y. That's x squared times y. Now here's the problem. In order to do calculus on this right now in Calculus 1, I have to turn this into a function of one variable, because that's the only calculus I know is calculus of one variable. So in the guidelines we saw something about a constraint equation. So for this one, the constraint equation comes about from the English that says the sum of the length, width, and height cannot exceed 108 inches. So the sum of the length, the width, and the height. So that's x plus y. Well, x plus y, that's 2x plus y. Now that can't exceed 108 inches. Well, let's just assume, let's logically assume that it's going to be maximized, the volume will be maximized when we go all the way up to 108 inches. So, to turn this volume into a function of one variable, so we can do calculus on it, why don't we solve this for y? Subtract 2x from both sides. Substitute that in here. We now have volume as a function of one variable, x, and it's 108x squared minus 2x cubed. This is exactly what it is. This is what we're trying to maximize. We're trying to maximize this volume. So now we know there's an interval. We can come up with an interval here. We're trying to maximize it on the interval. Well, let's think what x is representing here. X is a dimension of the base. X can't be a negative number. Can't be a negative number. So I'm kind of piecing this together. X has to be a positive number. So let's start off with, x has to be a positive number. I suppose we could say x could be 0. That wouldn't be much of a box now, would it? but let's not. Let's say x cannot be 0. I mean, if you have a square base that's 0 by 0, I mean, you're not gonna have a box. So now what's the largest that it could be? What's the largest value x could be? Well, we know 2x plus y, the most it can be is 108. So half of 108 is 54. So if I made this side 54 and this side 54, then my height would be 0. Again, that's not much of a box. A 54-inch by 54-inch, what, just a piece of cardboard? I don't know. It's not much of a box. So x can't be larger than 54, and I don't think x can even be 54 because you wouldn't have a box. Folks, we have an open interval. I can't use the techniques of finding an absolute maximum on a closed interval that we saw earlier in the chapter. This is where the power of the second derivative test will come into play the game. So let's continue. We're trying to maximize this on that interval. Well, we need the derivative. So the derivative is 216x minus 6x squared. We need to know where the derivative is equal to 0, so we set the derivative equal to 0. And over here on the right-hand side, well, you know what, I could just factor out an x. And I set each factor equal to x, so we get x is 0, or 216 minus 6x is 0. So, you know, add 6x to both sides, divide both sides by 6, we get x is 36. Okay, this one doesn't make any sense. It's not in our interval, so I don't care about it. Now, because I have an open interval, this is where the power of the second derivative test comes in. This is a value of x where the derivative is 0, which means if you look at the graph of the volume function, there would be a horizontal tangent line. The second derivative test says compute the second derivative. Okay, the second derivative is 216 minus 12x. Evaluate the second derivative at the critical number where the derivative is equal to 0, so we only have one, it's 36. So evaluate the second derivative at 36, and if you do that, I think you get something like a negative 216. It doesn't matter, you get a negative number. Because it's negative, that means the graph would be concave down. Concave down means that at this value of x, you're at a maximum. So this tells us we are at a max at x equals 36. That's where the power of the second derivative test comes in. And if we, let's see, answer the question, Bill. What are the dimensions and the volume? Well, the dimensions. We know x is 36 inches, so this is 36 inches. So the dimensions. 36 inches by 36 inches. 36 by 36. The height, well, I take 36 and toss it in here for x to tell me what y is. That's the height. So 108 minus 2 times 36, I think that gives me 36. So actually it's a cube that would maximize the volume. And then the other question is what is the maximum volume? Well, the maximum volume 36 times 36 times 36, which gives you 46,656 cubic inches. Alright, so typical optimization problem. I picked one that had almost everything involved in it, about as nasty as it could get. I picked an open interval, which meant we had to use the second derivative test. Folks, if I have a closed interval, I'm using the techniques we learned earlier in the chapter, that 5-step process of finding an absolute max or an absolute min. But here I picked one where we couldn't do that. So that's it. I said we were only going to do one example because I can't do an example of every type of optimization problem. This is up to you. You have to read the problems carefully, and you can do that. You can do these problems. So I didn't assign very many, here in section 4.5, but you can head off now and do the exercises. So go do the homework in section 4.5. Thanks for watching.